David Spears, civil engineering instructor at Texas Tech University, talking about static C2301. We've got a 2D rigid body equilibrium problem. Kind of some interesting geometry going here, and a roller on a slope at point D. So you can see the setup here. I've got a 500-pound force up in the upper left-hand corner at B at a 345. I've got a 708 foot-pound concentrated moment, pure moment. It's a couple moment acting at C. And then at D, I have a roller on the right end on a 12.5 slope. So that's going to be part of our things we have to look at to solve the problem. I want the reactions at A and D. And so, of course, the first step on any of these problems is to draw a free body diagram. Draw the L-shaped bar. At A, it's easy. I just have AY and AX. Everybody knows that. I have 3 feet to this 500-pound force at a 345, so it's more horizontal than it is vertical. So it's 500 pounds. I draw that on there, 345. And at C, I have this couple moment, which is a pure moment. It doesn't matter where it's located. I'm told that point C is 3 feet from the left end, but it doesn't really matter because wherever it's located, it tries to rotate that rigid body with 708 foot-pounds of rotational force or moment. Label that with its value. At D, what I've really got is very interesting. I've got a roller on a slope. So I know that a roller exerts force perpendicular to the slope. So I can kind of draw it right there and just call the force that the roller exerts one force, D. But I need to be able to get it into Cartesian components. So I've drawn this triangle up here to analyze the force and figure out how the relationship works. Okay, so if I've got a 12.5 slope, I've got this angle theta here adjacent to the 12 side, and by similar triangles I can draw that same relationship with theta down here, because that line there on the bottom side of what's forming a triangle is perpendicular. It's parallel to the x-axis, which is the same thing as 12 up here in the slope diagram. Well, I say that the roller support acts perpendicular to that, so I can draw this perpendicular angle. I can say that angle is perpendicular in that upper corner of the triangle I've drawn. Well, if I've got 90 degrees there, perpendicular, theta here, that makes this angle down here in the lower right-hand corner 90 minus theta. If that's 90 minus theta, and I want to now get the slope diagram on the force D, now I form another triangle right here, and I want the slope, the horizontal and the vertical. So I've got a right angle right here, a 90-degree angle in that left corner, that little small red triangle. And if I know that this is 90 minus theta in the right-hand corner, then by the way triangles work, that angle has to be theta. So what I can say is that if I have a force that's perpendicular to a 12.5 slope, what I've got is a 5.12 slope like that for the force itself. So I want to put that information over here on the force, which is 12 and 5. So of course that's a 12, 5, 13. So I'm ready really now to get everything in Cartesian format. Going back to this one last time, if I've got an angle theta with a slope to the horizontal, then the perpendicular force makes an angle theta to the vertical. So if I've got a slope at an angle theta, then perpendicular to that creates a force that is theta to the vertical, if that force is perpendicular. It's going to be useful to know as we do other problems in this class. Okay, now I want to get everything in Cartesians on my free body diagram. So here at the 500-pound force, I draw the y and the x. The y is the 3/5 of the slope. 3/5 of 500 is 300 pounds. The x is 4/5 of 500. That's 500 pounds. 400 pounds. I do the same thing with the force at D. Get an x and a y components. The horizontal is 5/13 of D. The vertical is 12/13 of D. Now I'm ready to just start doing some math. And I want some moments about point A, so I can just solve for one unknown, the force at D. So I want to sum moments about point A. I want to say counterclockwise is positive. It's equal to 0. Of course, it eliminates AX and AY. It also eliminates this 300-pound force because it intersects point A. So all I've got to worry about is the 400-pound force, which is trying to rotate clockwise about point A. So by my sign assumption, it's negative. It's an X force, 400 pounds, and a Y distance of 3. Then I've got my concentrated moment, my couple moment at C of 708. It doesn't matter where it's located. And it's trying to rotate clockwise, so it's a negative by my sign assumption. Note that this is pounds and this is feet. Well, the 708 already has pounds and feet in it. So it doesn't matter where it's located. The distance doesn't matter. I go over to point D. Both of those components create moment. The 5/13 is trying to rotate counterclockwise, so it's positive 5/13. D is the force. The distance is that 3-foot distance, that Y distance. Then I've got the 12/13 also trying to rotate counterclockwise, so it's positive 12/13 of D. That's a Y force. X distance is 12. So now I can do all the math. I get negative 1200. 400 times 3 minus 708. This works out to be 15/13, 5 times 3, divided by 13D, plus 12 times 12, or 144 divided by 13D. I can combine those two terms and I get negative 1908, plus I do the math and I get the decimals on it, and it equals to 12.23 D, which is 159 over 13 is 12.23 D. Rearrange and solve for D. D is equal to positive 1908 divided by 12.23, which is equal to 156 pounds. The positive means the direction I assumed is correct. It's up and to the left on the bar ABCD. Once I know that, the other two are pretty easy. Sum of the forces in the x direction equals 0. Positive is to the right. I have AX. I have the 400 pounds from the 500-pound force at B. And I have minus the x component of the force at D, which is 5/13 of 156. That's the force at D. Rearrange, do the math, I get AX. Negative 5/13 times 156, so that works out to be 60. So I get 400 minus 60, so I have AX plus 340. If you do the math, therefore AX equals negative 340 pounds. The negative means it's the opposite of my assumption, so it's to the left. And finally, I have sum of forces in the Y equals 0, positive is up. I have AY. I have the negative 300 pounds component of the 500 pound force at B. And I have acting up the 12/13 part of the force at D, which is 156. And that equals to 144 pounds, 12/13 of 156. So I have AY minus 156. If I combine the negative 300 and the positive 144, that equals 0. Therefore, AY is equal to positive 156 pounds. Positive means up. I have that force. Now on these 2D rigid body equilibrium, it's often easy to check it with the moments about another point. Check your answers. Check with sum of moments about point D. Counterclockwise is positive, and I've got 300-pound force at B trying to create counterclockwise rotation, so it's positive 300 times 12. I have the 156 from AY trying to rotate up, which is clockwise, so it's negative 156 times 12. I should probably reverse this arrow on my free body diagram for AX. It's going to the left, which is going to create clockwise rotation about point D. So it's clockwise, so it's negative 340 times 3. And then I've got to consider that 708, which is also clockwise, doesn't matter where it is located. So it's negative 708. So I can do all the math, and I get, this is 3600, and I didn't do the math here. Anyway, that all works out to be 0, so check.